These are the Chapter 1 notes. We're going to just talk a little bit about what chemistry is. The other thing I want to mention, I did post the Chapter 1 homework. How many of you get a notification every time something changes on Classroom? Did you hear a little dink this morning? I try to put the homework on Classroom, and the back side of this board is also where I keep ongoing assignments for physics and chemistry. You're always welcome to screenshot this if it's easier for you, but I do tend to try to put it on Classroom. So right now my projection is that the homework for Chapter 1 will be due next Monday. So I'm giving you almost a week's lead, and I'll give you some time here and there to pick away at it. In the interim, we will also be doing a lab. We'll probably do our lab on Thursday, because I can't imagine, because we're off. Today's your double day. Tomorrow's a single day. So we'll probably do the lab Thursday. And it is a lab doing some physical separations. So, with that, let's get started. Chemistry is one of the physical sciences. The other one is physics, but this is the easier physical science. And chemistry is really just the study of matter. The composition of matter, how matter is structured and shaped, the properties of matter, physical and chemical, and the changes that matter undergoes. The main ways that we get information in chemistry are through direct observation and measurement. It's not so much theoretical. There are sciences where we have a lot more sort of thought experiments. Chemistry is pretty hands-on. We can directly observe matter, and from those direct observations, we can very often make inferences about what's happening or what that's demonstrating at a little tiny level. So we see things at a macro level that give us information about what's happening at a actually sub-microscopic level. You can't see atoms with a microscope. Let me ask you this. Is everybody clear about the difference between an observation and an inference? This is something that comes up in biology very often, and people kind of trip on it. So if I say the windows are wet, is that an observation or an inference? It's pretty observational. I can actually see beads of water on the outside surface of the windows. That's an observation. If I say it rained this morning, is that an observation or an inference? It's an inference. It's not raining right at the moment that I can see. The pond appears to be still. No water is hitting the windows. Is there some other possible explanation for the fact that there's water on the windows? Yeah, somebody could have taken a garden hose out there this morning and hosed down all my windows. But I'm inferring from the appearance of the entire misty, moist world out there that it rained here this morning. That's an inference. So just to be clear, an inference is a conclusion that you're drawing from observed facts, where an observation is information that you're getting directly with your senses. Okay, branches of chemistry. Your book discusses 6 branches of chemistry. 7? 6. Organic, inorganic, physical, analytical, biochemistry, theoretical chemistry. Of all of these, there are only 2 that I'm really interested in making sure that you are familiar with. Organic and inorganic. And organic chemistry is not like organic carrots. Actually, it's pretty much the exact opposite of that. Which is why chemists sometimes laugh about the idea of organic produce. And I say that as an organic gardener and a chemistry teacher. Organic chemistry is all about compounds based on carbon. Those are what we call organic chemicals. Most of what we might also call polymethyl bad stuff occurs under the heading of organic chemistry. There's lots of really nasty stuff in the organic world. Gasoline is an organic chemical. Put gasoline on your organic carrots and they're dead. Doesn't work. So organic chemistry, it has some sort of sub-branches, but carbon-based compounds come out of organic chemistry. Inorganic is what we do here. We'll talk a little bit about some carbon-containing compounds, but for the most part we're talking about inorganic chemicals, which are things made of metals and non-metals. They're not necessarily based on carbon. And that's what, if you are going on to anything that requires you to do a year of college chemistry, it's inorganic. general chemistry is inorganic chemistry. Organic chemistry is a special thing. Who here thinks they will take chemistry in college? Nursing, med fields, okay. Usually, biology majors, a lot of science majors have to take 1 year of chemistry at state schools, I know, at the private schools, I'm not so sure. And generally that is a year of inorganic chemistry or general chemistry. Okay, physical chemistry, study of property and changes of matter. Yeah, and it goes a little bit beyond that in college. Analytical chemistry, we'll do a little bit of analysis hopefully at the end of the year, but that's where you're looking at unknown compounds, you're trying to figure out what they are based on characteristics. Biochemistry really is almost a subset of organic. Have you ever heard yourself called a carbon-based life form? You are. Such splendid carbon-based life forms on a Tuesday morning. You're carbon-based, and so a lot of the chemicals that have activity in your body, be it hormones, be it drugs, be it all kinds of signaling messenger chemicals, tend to be carbon-based. And so while biochemistry is not organic chemistry, a lot of the chemicals that you study in biochem are actually organic chemicals. So they're carbon-based. And then there's theoretical chemistry, and that's much bigger. Gesundheit. You're using a lot of math and a lot of computer modeling to understand how substances behave and to understand the underlying physical principles behind how substances behave. As I said, the only two that I really want to make sure that you know are organic and inorganic. Those are the two that you really need to be aware of. So mass, and you've probably known this since middle school somewhere, anything that has mass and takes up space. And mass is actually the amount of matter. Weight is different. You know this distinction, I think. Weight is how attractive you are to the earth because it's the force of gravity pulling on you. If you eat a lot of Christmas cookies in the month of December, I generally am far more attractive to the earth on January 1st than I was on December 1st because I really like Christmas cookies, and that makes me more attractive to the earth. I gain weight. Actually, I add mass to myself by eating Christmas cookies. And then the earth finds me more attractive. The earth exerts a larger force on me. So that's the distinction between mass and matter. And you've taken the quiz, hopefully, or you will be doing so in the next 24 hours. Yeah, not a whole lot of people took it. Okay. We will talk a whole lot more about atoms. Okay, so we're going to talk a whole lot more about atoms this year, but for now, and you probably remember this from physical science, they are the building blocks of matter. They're the smallest things that have the properties of the element of which they are a part. And at one time we thought you couldn't divide them. We know better. We'll talk a lot about subatomic particles this year, but there they are. Okay, an element is a pure substance. It's made up of only one kind of atom. And here's the other easy way to remember this. If it's an element, you're going to find it on here. There. You're going to find it on the periodic table. It's going to pop up any second, I'm sure. If it's not on the periodic table, it's not an element. Period. Ha ha ha. Yeah, it wasn't all that funny, but it's the best I've got. If it's a compound, it's made up of two or more elements, and they are chemically bonded. Compounds are also, we could add electrically neutral, so they're made of atoms of more than one type of element, and they are electrically neutral. I have a lovely compound right here, sodium chloride. What two kinds of atoms is sodium chloride made from? Sodium and chlorine, yeah. Exactly. And we can bond lots of different elements together. Water, of course, is hydrogen and oxygen. Compounds very often have very different characteristics than the elements that they are made of. This is pure aluminum. This is nothing but aluminum atoms, all bonded together, and we'll talk a little bit more about properties of metals later on that explain why we can do this to it. When we talk about properties of matter, and we're going to use this aluminum as an example, The first sort of breakdown that we do on this is extensive versus intensive properties. Extensive properties depend on how much of this stuff there is, and they change when the amount of this stuff changes. So, one extensive property of the pure element that I gave you at your desk. Go for it, Emma. You were the last one seen with aluminum in your hands. So it would change if I took away half of your aluminum. What property would change if I took away some of your aluminum? You can phone your island compatriots if you would like. You can discuss it. Actually, discuss it at your islands. What's a property of this piece of aluminum that would change if I took away half of the aluminum I just gave you? Go ahead, you're allowed to talk to one another. And then I spy on you and listen for murmurs. I heard murmurs of mass, which is correct. If I tear the aluminum sheet that I gave you in half and take away half of it, the mass of the aluminum sheet has changed. That's easy to understand. The volume of the sheet would have changed too. We could calculate the volume of this sheet. It'd be a little bit of a pain in the butt, but we can do it. Energy is a weird one. So let's talk about this a little for a moment. Does this sheet of aluminum laying on your desks have energy associated with it?
Yes.
Yes, it does. What kinds of energy? You remember any of your energy stuff from physical science? Yeah.
Potential?
Well, depending on where it's situated, sure. If I put it up here, it's got more potential energy than if I lay it on the floor, yeah. If we took away half of the sheet again, would that reduce its potential energy? Yeah. But we could also reduce its potential energy by moving it positionally. Touch that aluminum, if you're not already. If you're a fidgeter, you probably have it in your hands right now. Does it feel about the same temperature as your skin? Does it feel notably warm or cold to you? Probably not. It's a metal. It's a great conductor of heat and electricity. It's taking heat from the room. It's got some thermal energy. It's got some thermal energy, and that depends on how many atoms are there. It's also got sort of chemical potential energy, which depends on how many atoms are there. So those are all extensive properties. Now, intensive properties, it doesn't matter if I take away all but the tiniest little scrap of your aluminum. The intensive properties aren't going to change. Has anybody here ever melted aluminum cans in a fire? Oh, it's so much fun. I had a student many years ago, whoops, there goes my aluminum, and his hobby, seriously, when I asked him at the beginning of the year, what should I know about you, any hobbies, his hobby was melting things. I kid you not, he melted lots of things. Every now and then he would bring me something and say, look what I melted over the weekend. That was just his thing. He was a fun guy. Could you melt this? Yeah. Aluminum is fairly easy to melt. It's got a relatively low melting point in terms of metals. Doesn't matter if I give you the whole roll or just a tiny square, the melting point is not going to change. Could you vaporize aluminum? Can it be vaporized, I should say, not could you do it? Yeah. It could be made into a vapor. It takes a lot more energy. Does it matter if it's this much or this much? No. The boiling point is going to be the same. Its conductivity, how many electrons it can conduct. Doesn't matter how well it conducts electrons, rather, whether you have a large sheet or a small one. That's not going to change. The density of the aluminum isn't going to change. And we'll actually do some density calculations with other substances a little bit later. But that doesn't change. Again, all of those are intensive properties. This is one of those things that should pretty much be reviewed from physical science. Physical properties you can observe without changing the substance. So, I have, if you've got your aluminum foil, onto your aluminum foil, I will add a little compound. There we go. There's your aluminum foil. There we go. I'll give you a little bit of this lovely little compound here. You'll want to hold on to that for later. This little compound, this sodium chloride, you know what, let's get that out of the fold before something disastrous happens. Okay, so a little bit of Sodium chloride there sitting on top of our aluminum. You could observe a lot of characteristics of this sodium chloride. Whew, that's a lot of sodium chloride there. You could try to melt it. Wouldn't be successful, but you could try. You could try to boil it. Again, not really something you can do in the classroom. You could test its density. You could observe its color. You could observe the size of the crystals. Those are all physical properties. Your observation of those properties isn't going to change what that stuff is. You could dissolve it in water. Is salt soluble in water? Yeah, which is fairly important. In the last lab, you separated salt and sand based on the solubility of salt. All of those are physical properties. Does dissolving salt in water change the chemical identity of the salt, of the sodium chloride? No. It's still salt, now it's just salt in water. That means that it is a physical property. A chemical property is something that when you observe it, it changes the matter. When you think about chemical change, you have new substances at the end. With a chemical property, your observation of the property is going to mean you're changing the substance. Burning, flammability, combination with oxygen, rapid combination with oxygen, releasing large amounts of heat and light. When you test the flammability of something, at the end you're left with a new substance. That means flammability is a chemical property. Reactivity, whether or not two chemicals will react. If they do, at the end you're left with a different substance. That means that that's a chemical property. Okay, this is going to get us to where we need to be for our lab. I'm going to shut up for a moment. If you're copying this, it's sort of a flow chart thing, but we're starting with just sort of general unknown matter. Okay, so when we look at matter, the first question we ask is, can we physically separate it? When we say, can it be separated, we here mean physically. So if you imagine a bowl of chocolate chip cookie dough, sounds pretty good to me, can you pick out the chocolate chips? Yeah. So you can physically separate the chocolate chips from the rest of the dough. That is physical separation. If the answer to can it be separated is yes, then it's a mixture. It hasn't chemically bonded. And then we look at, is the composition uniform? This is where we get back to those prefixes homo and hetero that you may remember from biology, from genetics. Hetero means what? Different. Yes. Different. Homo means same. So, homogeneous mixtures are the same throughout. You're sitting in a mixture. What is it? The atmosphere. You're sitting in a mixture. So have you guys heard, I don't know how many of you listen to the news, have you heard about the epidemic of nitrogen pockets? It's fairly terrifying. So can you see the gases in the atmosphere around you? No. We can't see the molecules of gas in the air around us. Which one of the atmospheric gases do you need to keep breathing? Oxygen, yes. That's the one we want. That's the one we like. That's about 21% of the atmosphere. So if you walk into a nitrogen pocket, Gesundheit, what happens if you get a couple lungfuls of nitrogen gas? You suffocate. You die. Because your cells aren't getting the oxygen they need. Your brain isn't getting the oxygen they need. So nitrogen pockets are a very, very real danger. Have you heard of these? People are walking along the street, they hit a nitrogen pocket, they just fall over dead. You haven't heard about this? It hasn't been all over the news? Why do you think it hasn't been all over the news? because I'm messing with you? That's a distinct possibility. Good morning. How are you? Avoid nitrogen pockets. The air, the atmosphere that we're sitting in, tends to be which kind of mixture? Homogeneous or heterogeneous? It's very well mixed. Fortunately for us, we don't have nitrogen pockets. It is a homogeneous mixture. The composition of the air throughout is the same. I take a deep lungful over here. About 21% of the molecules that I'm getting into my lungs are oxygen. I run over here. I do the same. About 21% of the molecules that I'm getting into my lungs are oxygen. Whew, no nitrogen pockets. This is good. In general, the atmosphere is pretty well mixed. So we tend to have a homogeneous mixture. Milk is a homogeneous mixture, well, as we usually get it at the store. You can buy a heterogeneous mixture of milk. We'll talk about that in a second. Who here has had Kool-Aid? Okay. Kool-Aid, if you're doing it right, is a homogeneous mixture. It's all the same sweetness throughout. It's all the same color throughout. There are no chunks on the bottom. It is a homogeneous mixture. You can have a solid mixture too. Actually, these surfaces here, the resins of the desk and the lab tables, are for the most part homogeneous mixtures. It's a mixture of chemicals that are bonded together and they make these artificial surfaces. Stainless steel is a homogeneous mixture. It's the same throughout. There shouldn't be any pockets with more of one element than another. Now, who here has ever had Baker's Dairy milk? My favorite. That's the way milk comes out of the cow. What happens if you leave Baker's Dairy non-what? Non-what? What's that word? Pasteurized. No, it's pasteurized. Pasteurization is a process where they heat it to kill bacteria. That's legally, you have to pasteurize milk in the state of Ohio. But there's another process. Homogenized. Baker's is non-homogenized. Baker's is a heterogeneous mix. That's the way milk comes out of the cow. Which part separates? The delicious creamy fat rises to the top because it's less dense than the sugars and proteins in the milk. Milk that you buy at the grocery store is homogenized. It has been made into a homogeneous mixture. So we could add to this list heterogeneous, Baker's milk, homogeneous, homogenized milk. Heterogeneous mixtures, there are lots of them. I've got a nice little chunk of granite over here, and it's heterogeneous. We've got, you can pass that around, chunks of different sized pieces of mica. If you look really carefully, you may see little bits of olivine and some other minerals in there. And they're different sized, and they're not all arranged continuously throughout. Your blood is actually a heterogeneous mixture. If we look at all the blood in your body, is it all evenly mixed? No. The blood exiting your lungs has a markedly high concentration of, what was that atmospheric gas we wanted? Oxygen. If we look at blood entering your lungs, it's got a very low concentration of oxygen. It should have been stripped of all its oxygen by your cells. It is heterogeneous. There are salts and hormones and other chemicals that flood certain parts of your bloodstream and that aren't in other parts. So it is heterogeneous. Okay, so that's our mixtures, heterogeneous versus homogeneous. If the answer to can it be separated is no, then what we're talking about is a pure substance, and there are two different kinds of pure substances. If we look at the two substances that you have on your desk, you've got aluminum, you've got sodium chloride. Can you physically separate the sodium atoms from the chlorine atoms? You can? I want to see it. No. No. Challenge accepted. You can't physically separate those two things. They are chemically bonded. It's an ionic bond. They're chemically bonded. And they're a compound. So sodium chloride is a compound. Sugar is a compound. Water is a compound. You would have to perform some sort of chemical reaction to separate those atoms. The aluminum that's on your desk is only one kind of atom. That's all aluminum atoms. That can't be separated because it's only one kind of atom. So the difference here is compounds versus elements. But they're both pure substances. Pure water is still pure water. And I can tear this down as far as I want. I am separating some atoms from one another, but the aluminum is all still aluminum. Pure substances. They have a fixed composition. That sodium chloride, which is relatively pure sodium chloride, it's food-grade sodium chloride, and I'll take the granite if you're done with it. Every single bit of sodium chloride, I could chase that all day. Huh? Every single bit of sodium chloride that you're going to find has the same properties. It's got the same melting point, same boiling point, same conductivity. And it's got the same ratio of sodium to chlorine by weight, by mass, by atomic mass. And no matter where we take it from. So I actually have this beauty. Check this out. Isn't that pretty? You know what it is? Mostly sodium chloride. I got to go to a salt mine under Lake Erie a number of years ago, about 10 years ago. It's 2 miles down under Lake Erie at Geneva. It's the Morton salt mine, and most of the salt that's mined there goes to rock salt, road salt. It's pretty dirty when it comes out. You can see the bottom here is a mixture of sodium chloride and ancient fish poop and ancient dead bugs and stuff. Pretty neat. But it was a sample, it was a tour for educators, and we were allowed to take samples out. Doesn't matter if the salt comes from the salt mine in Geneva, if it comes out of the ocean and someone evaporates the water off. It doesn't matter if it comes from a mine in Scotland. It doesn't matter if it comes from a salt mine in Utah. The sodium chloride is identical. It's got the same composition, same ratio of sodium to chloride. So if something is a mixture, it can be physically separated, and we're going to talk about 4 different ways to do separations. Here's the key component. Separations are based on differences in physical property. So manual separation is based on particle size and appearance. If I give you a bowl which is a mixture of sugar and salt, would you have an easy time separating that? No, not manually, because they look the same. They both look like white crystals. So a manual separation has to be based on a difference, a visual difference. How many of you had Mr. Voorhees? I think he does the magnetic physical separations, and he does a magnetic separation where you have iron filings in sand. Okay. That magnetic separation is based on a difference in magnetic attractiveness. Sand is not magnetic. Iron filings are. So you can separate them based on that difference in their physical characteristic. Magnetic attraction being a physical characteristic. Filtration. You've done this. Hey! You did this. How cool. Filtration is based on a difference in solubility. So solubility is the ability of a compound to dissolve in a solvent. Salt is very, very soluble in water. Sand is not. If sand was, your experience at the beach would be a whole different thing. If two substances have different solubility, you can separate them via filtration. And that means you have to add a solvent to them, dissolve the one that's soluble, and then run that through a filter of some sort. You're going to use this in the physical separation lab. Okay? You're going to use solubility differences to separate two substances. Water is not the only solvent we can use. Who here has ever done wheel bearings? Darn it. Okay. Cleaned up greasy parts. Really? Gotten grease on your hands? Yay! Okay, grease on the hands. I'll bring in some grease. You can all have experiences. Does water take off dirty grease real well? No. What do you use? You can use some dish soap. You can use, we keep Gojo in the garage. You can use something like Gojo. Because greases and fats are not water soluble. You know this because you know that if you make salad dressing, the oil and the water don't mix. The oil floats to the top. It's not soluble. There are things that are not soluble in water, but that are soluble in other solvents. Okay, so there are substances that are soluble in alcohol but not water. There are substances that are soluble in fats but not water. There are substances that are soluble in things like gasoline or diesel fuel in organic solvents but not water. When you're looking to separate two things, you're always looking at differences in solubility. Okay? Heating is the last one, and you're going to use this also in the physical separations lab. When we talk about the heat of vaporization, that is the heat at which what happens? Vaporizes, becomes a vapor. Goes from being a liquid to a vapor, to a gas, or in a few cases goes straight from being a solid to being a gas. Do you know what we call that? We haven't talked about phase changes yet. It's subliming, sublimation, when it goes straight from being a solid to being a vapor. Okay, if you have two things that have very different heats of vaporization, you can boil one off, and in some cases capture it. Distillation is a physical separation based on a difference in heat of vaporization. What is distillation? Do you know? You're purifying, typically purifying water. So if I have water with a bunch of other stuff in it, I can boil that water, capture the steam, and recondense the steam, and then I have pure water, nothing but water. You can distill and purify alcohols. This is, the old Kentucky. Well, isn't there now a TV show about like people running stills up in the hills? Okay, that's all it is. It's chemistry, folks. You're boiling off alcohol, which has a lower boiling point than water. You're collecting the vaporous alcohol and recondensing it into a more purified form of alcohol. So you're separating out the water. Gasoline and diesel and all of our organic chemical fuels go through a distillation process to purify them. You get out the stuff that has different boiling points and vaporization points. Okay, with that, I'm going to ask you to do the following. Because the stapler is out of staples, it paused and didn't print, and then when it finally did, it didn't put them together. So you get to have the fun of going 1, 2, 3, 4, staple. At each lab table, you will find one page. Your job, start at the back, move to the front, put them in order, staple them, and then we'll talk about your procedure. Okay, you got the lab here. This lists a couple of different kinds of separation and some terminology. You're not responsible for putting that in your pre-lab summary. You just have to do the procedure. But I do expect you to know those. The thing that you are responsible for doing before we start the lab on Thursday is looking up the characteristics of your materials.